Hello student, welcome to my channel The Learn Physics. Today I will be discussing the magnetic effect of current, that is Oersted experiment, magnetic field lines, properties of magnetic field lines and representation of magnetic field with the magnetic field lines. Then magnetic field due to a straight conductor, due to a circular coil, magnetic field due to a solenoid, comparison between a solenoid and a permanent magnet, then electromagnet, then force on a current carrying conductor in a magnetic field, then Fleming left hand rule, and finally electric motor. So this video will be extremely beneficial for you. Please like, comment and share the video. Okay? Now let's start. First of all, magnetic effect of current. Look at this. Suppose this is a conductor. Current passes through it by a battery. Look at this. If a magnetic needle is placed near the conductor, the magnetic needle deflects. As magnetic needle deflects, so there is a magnetic field here. Because magnetic needle is a very small magnet having north pole and south pole. The magnetic needle deflects, therefore magnetic field around the conductor is produced by current. That is, when current passes through a conductor, a magnetic field is produced around it. This phenomenon is known as magnetic effect of current. Now to understand the magnetic effect of current, first of all we have to discuss the magnetic field lines. Look at this, this is a magnet. It has a north pole and south pole. Now magnetic field lines emerge from the north pole and finally merge at the south pole, and inside the magnet it moves from south pole to north pole. Okay, look at this. In this way, okay, this is the magnetic lines of force. Now, properties of magnetic lines of force. Magnetic lines of force are imaginary lines which emerge from the north pole and merge at the south pole. Okay? The tangent at any point of these field lines represents the direction of magnetic field. Okay? The two magnetic lines of force never intersect each other. If they intersect, suppose this is the two magnetic lines of force, if they intersect, at the point of intersection, two tangent can be drawn, which represents two directions of a magnetic field at a given point. This is impossible. Okay? Look at this. The number of lines of force passing per unit area represents the magnitude of magnetic field. That is, if the magnetic field lines are close to each other, then the field is strong. And if the fields are far away from each other, then the fields are weak. Look at this. These field lines are equidistant and parallel. So this represents the uniform magnetic field. Okay? Understood? Now right hand thumb rule. Suppose this is a conductor carrying current in upward direction. Thumb represents the direction of current flow. Then other finger rep the conductor represents the direction of field line. This is a straight conductor carrying current upward direction. So look at this. This is the direction of lines of force. Okay. So magnetic field at this point directed along this direction. Magnetic field at this point directed this point. Magnetic field at this point directed this direction. Magnetic field at this point directed in this direction. The magnitude of magnetic field due to straight conductor depends on B equal to mu naught I divided by 2 pi r. That is magnetic field directly proportional to the current through the conductor, and magnetic field is inversely proportional distance of a point from the conductor. Okay, so greater the distance from the conductor, the magnetic field is weaker. More current flow through the conductor, the magnetic field is stronger. Okay, understood? Now magnetic field due to circular coil. Now look at this. This is circular coil of radius r. Current I pass through it. Number of turn in the coil is n. The magnetic field due to circular coil depends on number of turn. That is, greater the number of turn, greater is the magnetic field. Depends on current flow through it. Greater the current flow, greater is the magnetic field. And radius of the circular coil, that is, greater the radius of the circular coil, smaller the magnetic field. Okay, understood? Now direction of lines of force. Look at this. If we hold the conductor this way, so look at this, the magnetic lines of force like this. Okay, this is the direction of magnetic lines of force. Now the side where current flow through the coil is anti-clockwise represents n pole. If the current in this coil from this side is anti-clockwise, then current in the coil from other side is clockwise. Look at this. Suppose this circular coil. If current through it is the clockwise from this side, then from this side it is anti-clockwise. So one face of a circular coil is n pole and other face is south pole. Now look at this. This is the anti-clockwise current. This is the n pole. Look at this. This is the clockwise current. This is the south pole. Therefore, a circular coil behaves as a seat magnet. Now one similarity and one dissimilarity of a circular coil with permanent magnet. Now similarity. A permanent magnet has north pole and south pole. Look at this. A circular coil also has north pole in one side and south pole in other side. What is the difference? Look at this. Strength of the magnetic field is increased by increasing current and number of turn. But magnetic field produced by permanent magnet is fixed. Okay. Now magnetic field due to a solenoid. Look at this. This is a non-conducting frame. Look at this. If an insulated wire wound on this in such a way that each turn is perpendicular to the axis of it, then it is called solenoid. If radius of cross section of the solenoid is negligible in comparison to length of it, then it is called infinitely long solenoid. The magnetic field due to infinitely long solenoid depends on number of turn per unit length. Okay, and it also depends on current passes through it. Now the magnetic field due to infinitely long solenoid depends on number of turn per unit length. Current flow through the solenoid and medium within the solenoid. Okay. Now look at this. The side where current is in anti-clockwise direction represents n pole. Side where current is clockwise direction, this is the south pole. So it is just like a magnet. Now, what is the similarity between a permanent magnet and a solenoid? Look at this. This is the permanent magnet and this is the solenoid. Look at this. One end of solenoid is north pole and other end is south pole. Look at this. One end is north pole and other end is south pole. Okay? Now, each turn of the solenoid acts as a sheet magnet. In the same way, each section of the permanent magnet also behaves as a sheet magnet. Okay? Look at this. The magnetic field inside the magnet is directed along its axis. In the same way, magnetic field inside the solenoid is also directed along the axis. Okay? Now, dissimilarity, look at this. Its polarity cannot be changed. Its polarity changed by changing the direction of current. Okay? Now, the strength of polarity is increased or decreased by increasing current and increasing the number of turns, but its strength is constant. It can be made in different shape, but its shape remains fixed. Okay? This is also called electromagnet. Look at this. If an iron core is placed inside the solenoid, then its strength becomes very large. Okay? And behaves as a electromagnet. Now, force on a current carrying conductor. Look at this. This is a conductor carrying current I and its length is L. And it is placed in a magnetic field of strength B. The force experienced by the conductor depends on number 1, strength of magnetic field. Number 2, current flow through it and length of the conductor. Look at this. This is the length of the conductor. Actually, magnitude of force is BIL. The direction of force is determined by Fleming's left hand rule. Look at this. If 3 fingers of left hand are arranged mutually perpendicular to each other in such a way that middle finger represents the direction of current, forefinger represents the direction of magnetic field, then thumb represents the direction of motion of the conductor or force. Look at this. This is the magnetic field from north to south. This is the direction of current. So force is in the downward direction. Okay? Understood? If the direction of current reverse, then force in the outward direction. If the direction of magnetic field reverse, then direction of force is also reversed. If both magnetic field and current both reverse, then direction of force or motion of conductor remains in the same position. Understood? Now, electric motor. First of all, definition. It is a device which converts electrical energy into mechanical energy. Principle is the Fleming left hand rule. Or if a current carrying conductor is placed in a magnetic field, then it experiences a torque. Now, components. First of all, field magnet. N and S are the 2 poles of a field magnet. The armature coil is rotated within the 2 pole pieces of the field magnet about a fixed axis. Okay? Number 2, armature coil. It is the rectangular coil of an insulated copper wire. It is rotated about an axis which is normal to the magnetic field. Look at this. This is the axis and this is the magnetic field. So axis is normal to the magnetic field. The armature coil is rotated about this axis. Okay. Now commutators C1 and C2. Look at these commutators C1 and C2 are rotates with the armature coil and they are in contact with brush B1 and B2. And finally, brush B1 and B2 are in contact with the electrical source and commutator C1 and C2. Now, commutator changes the direction of current in the armature coil for every half rotation of it. Now, look at this. Suppose initially current passes through this direction. So, this current passes through B1 to C1, C1 to in this path. Look at this. So, according to Fleming's left hand rule, look at this. This is the This is the magnetic field. This is the direction of current. So, this is the force. Force is in inward direction. So, look at this. AB experiences force in the inward direction. Now, what is CD? Look at this. This is the magnetic field. This is the current. And CD experiences outward. CD experiences outward force. So look at this. AB experiences inward force, CD outward force. So it starts turning. After half rotation, look at this. C2 is in contact with B1 and C1 is in contact with B2. So position of CD here, this position, and AB this position. Look at this here. After half rotation, the position of CD and AB interchange. And here now after half rotation, B1 is in contact with C2 and C1 is in contact with B2. So direction of current, look at this, B1 to C2, then from D to C to A and B. Look at this. Here CD experiences inward force and AB outward force. So it starts turning. So look at this. At every half rotation, the direction of current in the armature coil changes. So armature coil rotates continuously in same direction. Okay? Understood? Many thanks for watching this video. This video will be extremely beneficial for you. Please like, share, comment on this, and don't forget to subscribe my channel to learn physics easily.